So we've seen examples of how we can use decision trees for classification, but we can also use them for regression. So in earlier lectures, you saw how we can use a logistic regression model for classification. In this lecture, we saw how decision trees could be used as an alternative for classification, but we could do the same thing, the same exercise for regression instead. So rather than using a linear model, we could build a regression tree. And so similarly, we're going to ask questions at each level. So we'll start with, let's say we're doing hiring. So we could say, first question is, does the person have prior experience? And if the answer is no, then the terminal node is the value $15 per hour. If the answer is yes, then the next question is how many years? And now in this case we have 3 endpoints, one that's less than 2, for which the terminal endpoint is $18 per hour. If it's 2 to 5 as the answer, then the terminal endpoint is $20 an hour. If it's greater than 5, then we have another node that we have to split. So here, the range of outputs is a quantitative prediction, right? It's a value, $15 per hour, $18 per hour, $20 per hour. And we could build bigger, more complicated regression tree models if we were using them for, let's say, real-world applications. Okay, so in summary, decision trees give us this alternative to a linear framework. So it's a non-linear framework that we can use for classification and, as we just saw, for regression. The way they work is fundamentally different from linear models, right? The decision boundaries we can create can be far more complicated, but that's both a plus and a minus, right? The minus here, the plus is accuracy on our training data. The minus is it doesn't generalize because we overfit. And so the risk of overfitting is very high with decision trees. Now, keeping that complexity under control, well, unfortunately, we don't have nice mathematical, provably optimal closed form solutions for how we do that. Instead, we basically use a bunch of heuristics, hard constraints on the size of the tree, or creating a full tree and then pruning nodes as we go. Random forests are kind of a balance, right? It's a very interesting application of bootstrapping, and it gives us very nice results. So when you look at machine learning more broadly, you'll see that there are many different conceptual frameworks for doing regression, classification, and other tasks. And so if you take classes like 189 or 188 or 102, you'll learn about linear models, decision trees, nearest neighbor, SVMs, support vector machines, Bayes nets, perceptrons, networks of perceptrons, that's neural networks and deep learning, and many other types of conceptual frameworks for doing regression, classification, and other tasks. So if you're interested in learning more about those, then I recommend taking a machine learning class, and they'll teach you them in very great detail. Now, how all of these work and the trade-offs of should I use an SVM or a neural network, that's beyond the scope of this class. Really what we're trying to do here is give you some of the most practical and useful tools for doing regression and classification.